Dr. T. Sangeeta completed her MSc Integrated course in Polymers from the University of Madras. Subsequently, she had completed in the year 2000 for the work Ziegler-Natta polymerization and awarded PhD. She also postdoc in SPIC Science Foundation and worked as R&D scientist in a fuel cell based company. Madam has also completed MBA in Technology Management and AMIE Materials and Metallurgical Engineering and also MA in Computer Integrated Manufacturing from Anna University in 2018. From the year 2014, Madam is working in Anna University, Chennai. Her Googler Scholar citation is 2582 with a high index of 27 and ITIN index of 67. Madam also granted for 3 patents for her research collaboration. She went to many countries, USA, UK, like that. Madam has completed 12 PhD candidates and also completed many sponsored projects, DST, DBT, BRNS, etc. For a research thirst, Madam has received Active Researcher Award in the year 2012 from Anna University. And she was also selected as one of the top 50 innovators of India by the DST Lockheed Innovation Growth Program in the year 2012. Madam also awarded for H. Nandi Memorial Award at the Indian Engineering Congress in the year 2014. She also the recipient of Women's Achiever Award in the year 2017 from Anna University. As a student's mentor, she was awarded twice for the Student Innovative Project in the year 2017 and consequently 2018 from the Department of Mechanical Engineering by CTDT Anna University. Ma'am has also received Wenlock Endowment Scholarship Award from the year 2016 to 17. With much pride, we welcome Madam to this forum to deliver her talk. Actually, Madam has accepted to deliver his talk on green technology. We welcome you, ma'am, on this forum.
Thank you so much, Dr. Kanimari, for giving me a brief introduction about my research and academic activities that I have come across all these years in this particular profession. Thank you very much. In fact, I have to give a very special thanks to Dr. Kanimari because I contacted her very recently. Having seen the topic in the website, I thought I have to reach the people through this particular faculty development program to give an information about the very scopeful and researchful activity that is going on in terms of renewable energy, particularly in fuel cell activities. Since I have been working in this field for a very long time, I thought I have to bring the challenges and the research limitations and other scopes that are available in this particular field. And I think I would make this particular session for the next 1.5 hours very interesting for all the candidates so that you take some information from me, which is going to be really useful for your academic and research activities in the future. Thank you so much. I think I can share my slides, Kanimari.
Yes, ma'am. Yes, sure.
Is that visible? Are my slides visible?
No, ma'am. Not yet, ma'am.
I don't know. Do you see now?
Yes, ma'am. Now it is visible.
Yeah. Yeah. Sometimes what happens in this Google Meet, if I go to the presentation mode, things does not happen well. I'll go to the presentation mode and then check. Otherwise, I'll be in this mode. Okay. Let me just check it up whether you are able to see the entire slide.
Yes, ma'am.
If it is yes, I will proceed.
Yes, ma'am. It is okay. Just scroll it, ma'am. Whether it is moving or not.
Yeah. I've gone to the second slide.
Yes, ma'am. Outline of this program.
Yeah. Third slide.
Yes, ma'am. What is a fuel cell? Yes, ma'am.
Then I'm comfortable. I will go with this presentation.
Yes, ma'am. It is okay.
Okay, thank you so much. I welcome all the participants to this faculty development program on green environmental activities. Okay, so this particular session, I'm going to talk about a very interesting topic called fuel cells, which is supposed to be one technology in terms of renewable forms of energy. This is a wonderful technology that has been developed for a long time. Since 2 decades, people are working out for this fuel cell activity, because it's a very good technology, and the concept that is available to prepare or produce electricity directly from any forms of chemical energy. So this is going to be really interesting, because the entire globe is going towards a concept or technology where the environmental pollution has to be brought down. At the same time, you have to have your electricity or any other forms of energy that is going to be utilizable for various activities of ours. Okay, so let us go into the topic of this fuel cell, a green energy technology. Here, although there are various types of fuel cells, I'm going to concentrate on one particular type of fuel cell, because I heard that we have zoology and biology based people and interdisciplinary kind of people are also attending this program. You will find it very interesting when I'm going to talk about this microbial fuel cell, which is a very good solution for not only making energy, a clean energy, because it's not going to pollute the environment. At the same time, you are reducing the pollution too. That is, I'm going to treat the water, the wastewater, which could be your domestic wastewater and industrial wastewater, or any other kinds of effluents that can come from any forms of industries, can also be treated simultaneously. So this becomes a dual solution for not only producing energy, but also treating the wastewater to make it more purer in the form. So that's going to be really interesting for you. The outline of my talk is going to cover what a fuel cell is basically, the basic definition, its principle and the working format, the different features or the attractive advantages with respect to the different types of fuel cells, and the types, the challenges that are ahead with this particular technology, fuel cell technology, and the approaches. And then we'll move on to a specific type of fuel cell called microbial fuel cell, and what is the need for it, how does it work, what are all the different components that are associated with, what are all the research activities with regard to the development of this microbial fuel cell that are existing globally, and why they are so importantly considered. Things like that will be dealt in detail in this particular lecture. Okay, so I will not read out all the outline parameters. Directly I'll go to the presentation. What is a fuel cell basically? We all understand it's an energy conversion device. Fuel cell is basically an electrochemical device. When I say an electrochemical device, some electricity is involved, chemical forms of energy is also involved. Battery is a simple energy conversion device where the chemical energy is stored in the battery and it is utilized for our requirement in the form of electricity. So this is an energy conversion device. Similarly, fuel cell is also an energy conversion device, which is an electrochemical device that reacts a fuel with the oxygen to form or to produce electricity. As simple as that. So you have a chemical energy directly getting converted into electricity, and this particular process does not involve any thermodynamic limits because there are no intermediate conversions. It's a direct conversion from chemical energy to the electrical energy. So that is one major advantage of the fuel cell. Another major advantage of fuel cell, it is not going to pollute the environment, because we all know that whenever a carbonaceous material or a liquid fuel that is being utilized for our various energy requirements, they burn, they get combusted, and then they form carbon dioxides and sulfur oxides and various other nitrogen and phosphorus oxides that are let out into the environment. Therefore, this particular fuel cell is a type of device where you don't have any of these SOx and NOx chemicals that are being produced. It's a direct conversion and it does not pollute the environment too. So these two important advantages of the fuel cell are making this fuel cell activity very, very scopeful for our various commercializations that are happening in the global level. The most commonly used fuel is the green hydrogen. Hydrogen is supposed to be called as a green form of energy because of the very reason that it does not produce any pollutants. It undergoes a combustion process with the oxygen as the oxidant and get converted into useful forms of energy along with a small byproduct, which is nothing but your pure water. So this water is the only byproduct in your fuel cell. So this fuel cell technology produces electricity, water and heat because of the combination of hydrogen and oxygen. So here you could see at the bottom, a picture is shown here. Hydrogen molecule combines with oxygen in the presence of catalyst. The presence of catalyst is very important, otherwise the catalytic reaction is not going to be favored at all. And remember, whenever I am making use of this hydrogen, this reaction is not as simple as what is shown over here, because hydrogen is a highly flammable gas. When it comes in contact with even a small concentration of the oxygen, it immediately explodes and undergoes a very highly exothermic reaction and produces a large amount of energy, and that's going to be a risky process. Therefore, this hydrogen combining with oxygen is taking place in a slightly different indirect manner. How this is going to take place, that's what we are going to see in the next slides. That's the basics or the principle behind the working of the fuel cell. But ultimately, the net reaction remains the same. The net reaction is that a hydrogen, which is nothing but a flammable gas, which is taken in the form of the fuel, combines or reacts with your oxidant. The oxidant could be anything. It is oxygen in this fuel cell, and these two combines in the presence of electrocatalysts, which are going to favor the reactions that are going to happen between this hydrogen and oxygen to ultimately form water as a byproduct and electricity, which is a major product which we are interested in, and a small amount of heat is also delivered outside. So look at this diagram. We can very clearly understand what is happening in the fuel cell device. So this is a fuel cell device. Here at the left, you could see that the hydrogen is coming from the tank and reaches the catalyst layer over here. This part, I call it as an anode. And the opposite side, you have the cathode. Any electrochemical device for that matter, we should know that there are three important components. One, the anodic chamber. Two, the cathodic chamber. And in between the anode and the cathode is the electrolyte. The function of the anode is, anode chamber is a place where anodic reaction is taking place. Generally, oxidation takes place in the anode. What is oxidation? Oxidation is nothing but a fuel is consumed to liberate or generate electrons. This loss of electron reaction, we call it as an oxidation reaction. And this oxidation takes place in the anodic chamber. Parallelly, simultaneously, a reduction process takes place in the cathode. Cathode, generally an oxidant is supplied, and this oxidant is going to consume the electrons, and this gain of electron is otherwise called as reduction. Therefore, you have simultaneously an oxidation process taking place in the anode and a reduction process taking place in the cathode. For facilitating the oxidation process, the electrons are generated out, which are coming from the hydrogen. And to facilitate the reduction process in your cathode, the electrons are going to be consumed. When the electrons are generated and consumed, their movement in the external circuit is nothing but the movement of the charge or the electrons, which is nothing but the current that is being produced. Wow, how this is happening in the fuel cell. Let us see this particular diagram very carefully. On the anodic chamber, you have hydrogen being supplied continuously. The hydrogen molecule H2 breaks down into protons and electrons. Protons are nothing but these H+ ions, and the electrons are nothing but these E-. These electrons take an external circuit to reach the cathode. Simultaneously, these protons, H+ ions, which are left out with the electrons from the hydrogen molecule, are going to transport or permeate through the proton exchange membrane in the middle. So what is this proton exchange membrane? This is basically a polymer membrane, an organic polymer membrane, which allows only the protons to get transferred from the anodic chamber to the cathodic chamber. The job of the proton electrolyte membrane, this proton exchange membrane is also called as an electrolyte. Anode, cathode, in between electrolyte. The job of the electrolyte is to allow only the ions to pass through, and no electrons are going to be passing through these membranes. So what happens? The hydrogen is split because of the presence of the catalyst. Generally, platinum is used as a catalyst. There are a lot of work that is going on to replace the platinum because you have to bring down the cost in order to make the fuel cell commercial. Therefore, there are a lot of activities going on. But as of now, platinum is supposed to be the best catalyst that is used both in the anode as well as in the cathode. So what is happening in anode? An oxidation process is taking place because of the presence of the platinum catalyst. The hydrogen molecule is split into protons and electrons. The protons take up the route through the proton exchange membrane and reach the cathode. Simultaneously, the electrons take the external circuit and they allow the resistance to be available here for the bulb to blow here, or any other features can be utilized here. So this movement of electrons in the external circuit is nothing but the electricity that is being produced. What happens in your cathode is these electrons, they reach the cathode and the protons also reach the cathode, and because of the presence of the catalyst and the supply of the oxygen, they undergo a reduction process here and then they get converted into water. And the water is going to be the byproduct, which is going to be coming in the form of a vapor, which is going to go out through the exhaust. So this is a very simple operation, working principle of any type of fuel cell by using hydrogen and oxygen as the fuel and the oxidant. So this hydrogen can be replaced by other fuels. Similarly, oxidants can also be replaced by other oxidants. Oxygen can also be replaced by other oxidants. But the basic principle remains the same. The basic principle is that oxidation takes place in your anode, reduction takes place in your cathode. There is a movement of electron in the external circuit from anode to cathode. There is a movement of ion. If it is a positive ion, they move from anode to cathode. If it is a negative ion, they are generated in the cathode. Therefore, they move from cathode to anode, depending on the case may be. The picture which is shown over here is allowing the protons along to transfer. What is the benefit of this entire working? I'm utilizing hydrogen as a fuel and I'm producing electricity. That's the benefit. So there is no direct combustion that is taking place as a reaction between the hydrogen and oxygen, as we have seen here in the previous slide. I told you in this first slide, hydrogen combines with oxygen in an indirect manner. Directly, they don't combine with each other. Therefore, there is no combustion directly taking place, but it is indirectly. The net reaction remains the same, but indirectly they are reacting to form the electricity, which is the very much wanted form of energy for our various uses. This is again a working principle of two types of fuel cells. One type, it is proton exchange material that is used. If you look at the first figure, it is called PMFC. PMFC stands for proton exchange membrane fuel cell or polymer electrolyte membrane fuel cell. In the first case, as we have seen in the previous slide, it is a protons or the H plus that are generated. Therefore, these H plus ions, they travel from the anode to the cathode. Suppose I have an alkaline membrane and these membrane are not going to allow the protons, but they will allow the negative ions to move through. For example, the hydroxide ions are shown in the second figure here. AEMFC stands for alkaline exchange or anionic exchange membrane fuel cell. In this case, it is a OH minus ion. OH minus ion is a negative ion. Therefore, generally they are produced in the cathode. They take up the opposite direction to travel, but the rest of the reaction remains the same. There's a slight change in the reaction. That is what is happening in your anode and cathode. Let us know about it in the next few slides. So what is it I want you to basically understand before moving on to the next slides is that in the first type, protons are allowed, and these protons are positive ions travel from anode to cathode through an electrolyte, and this electrolyte is a one which separates the anode and cathode as well as allows the ions to flow through. If it is an AMFC case, the same electrolyte is allowing the negatively charged ions to flow through. Therefore, they allow the ions to move from cathode to anode. Depending on the different types of fuels and oxidants, the different ions are to be used in these two types of fuel cells. So having understood that, we will move on to some basic features and then go on to the importance and the scope of this particular topic and the research challenges that are available. Coming to the attractive features of the fuel cell, I told you in the very beginning, fuel cell is a wonderful concept. It's a clean energy concept. It does not produce any pollution to the environment. It's of very high efficiency too. Whenever you take a carbonaceous fuel, for example, a wood or a petrol or a diesel material, they have carbon as well as hydrogen content with them. So this carbonaceous material, when they are combusted, they get converted to CO2 and CO and H2 and all other volatile gases that could be produced that could be harmful to the environment. But here, what is being used generally, very commonly, is your hydrogen. This hydrogen is entirely utilized. They are entirely converted into electrons or electricity. Therefore, the output product, electricity, is directly obtained, and the only simple byproduct is H2O, which is nothing but your water. Therefore, it is a wonderful clean energy technology, and as well as it is a high efficiency technology because the entire energy that is available with the hydrogen molecule is what is utilized for our fuel cell activity. So here the efficiency is also very high because you don't have other bonds that are present in the fuel that is used as a fuel in the fuel cell. And there are no wastage, of course. We have already understood this by having looked upon the principle of the fuel cell. And zero emission again, there are no polluting emissions, and it could be an indigenous source. Issue of national security is very much spoken here, because you don't have to depend on Gulf countries and other countries for depending on the various forms of your fuels. You can be indigenously preparing your fuel, because hydrogen is a gas which can be produced from various sources indigenously itself. You don't have to depend on your petroleum refinery making countries. And it is a simple concept. We have already understood. The net reaction is very simple. It's of promising low cost also. The cost factor when it comes to the fuel cells, it is the cost because of the hydrogen, and it is a cost because of the catalyst, and it is a cost because of the electrolyte membrane. These three materials, these three important components which are required for the functioning of the fuel cell, if there is a way to reduce the production cost, then it is possible for the fuel cell to become a more cost-effective process, along with its energy efficient and clean energy concept. And the next attractive feature is your no moving parts and no noise. This is actually put over here because we all know that in automobiles we have internal combustion engines that are being utilized for producing energy for our automobile or the vehicles to move on. So here the fuel is given over here with a particular fuel air ratio. The cylinder piston is going to be operated for different strokes. So here there are a lot of noises that are produced because of the moving parts there. Such moving parts are definitely not available in the fuel cell setup, and therefore there is no noise pollution also. And this is another attractive feature of the fuel cell. And they are modular in nature. The word modularity means this fuel cell can be made in a very small power range to very high power range. For example, you can make microwatt powers, you can have kilowatt powers, you can have megawatt powers, depending on the size, depending on the number of cells that are going to be used for your particular application. The range of wattage can be varied from very small value to very high value. For example, if I have 5 by 5 square centimeter, this is 25 square centimeter fuel cell, it's one small unit where you can supply hydrogen, you can have oxygen, and you have an electrolyte, and the reaction takes place and you can generate the electricity. So this can be even made down to a very small 1 by 1 square centimeter. It can be increased to meters square centimeter. Therefore, the size of the fuel cell can be increased. Similarly, the number of cells can also be increased. This can be highly compared with a battery. In the case of a battery, you have number of cells put together. Therefore, you can have 1, 2, 3, 10 or 20 number of fuel cells put together, and then you can increase the wattage. Basically, the number of cells increases the voltage, and the size of the cell increases the current. Current multiplied by your voltage is going to be your VI, which is nothing but your wattage. So if you are interested in increasing or decreasing the power output, you can play with the size and the number of fuel cells that are going to make up your fuel cell stack that is going to be utilized for your fuel cell applications. And then the next point is, currently with the desire to decrease the dependence on the fossil fuels, we all know that the fossil fuel is getting extensively used, and it is going to be extinguished in few years, and therefore this will have to be finding out new renewable forms of energy, wherein the wind energy, solar energy, hydroelectric energy, all these are playing a great role in bringing the renewable forms of energy. Under this list, you have the fuel cell also being dominating in the near future. And then the emission of these NOx and SOx and CO gases are not going to be there. And this point, I think I have discussed you very well in the previous slides itself. One basic question it always arrives in our mind. What is the basic difference between a battery and a fuel cell? Both of them, they have the capacity to convert the chemical energy into electrical energy. The basic difference is given over here in this chart. In a battery reactants are self-contained. The chemical form of energy is self-contained. It is not openly flowing. It is there in a stable condition. Whereas in the case of fuel cell, the hydrogen and oxygen are continuously supplied. It's open process. As long as you supply the hydrogen fuel into the fuel cell, so long as you will be able to producing the electricity. So this is not a contained form or a stationary form of the fuel cell. It is an open type and it's a continuously running one. Therefore, whenever there is a demand, you keep supplying the fuel, you keep producing the energy. But in the case of batteries, it's utilized. Or once the entire chemical energy is utilized, then you have to throw it out if it is a primary battery. And if it is a secondary battery, you will have to recharge it again, once again to fill up the energy into the battery. So this is a basic difference between the battery and a fuel cell. Then, now let us move on to the different types of fuel cells. How these fuel cells, the basic principle we have understood in the previous slide, how they are different from each other. What is the need or the scope for the different types of fuel cells? That's what is seen in this slide. The fuel cells are different based on the different types of fuels and the different types of oxidants that are going to be utilized to produce the electricity. Means that there are different types of electrolytes or the separator or the medium which is placed between the anode and cathode. So this also I have pointed out in the previous slide. If it is acidically conducting, if it is proton conducting or cationic conducting, I will have to have an electrolyte which is a cation exchange membrane. If it is going to be conducting the anionic ions, it will have to be anionically exchanging anionically exchanging electrolyte membrane. So depending on the electrolyte, you can classify them as positive and negative, acidic and alkaline type of electrolytes. The entire nature of the electrolyte determines all the important characteristics and the components that are going to be utilized in the fuel cell, particularly the operating temperature. Certain fuel cells, they operate at room temperature. Some fuel cells, they operate at 100 degrees. Some fuel cells, they operate at 1000 degrees Celsius also. So depending on the operating temperature, the component materials will have to be chosen. Materials of constructions will have to be chosen. And the varieties of fuels are also feasible to be given as a fuel in different types of fuel cells. So accordingly, these are all the different types of fuel cells. The first simplest form of fuel cell is proton exchange membrane fuel cell, otherwise called as polymer electrolyte membrane fuel cell. This is because the polymer membrane is the one which is used as the electrolyte in the proton exchange PMFC, PEM fuel cell. The second type is direct methanol fuel cell. This is shortly called as DMFC. Here, as the name specifies, hydrogen is replaced by methanol. Why a methanol has to be replacing the hydrogen? There are a lot of risks that are associated with hydrogen. I've told you in the earlier slides. Hydrogen is a highly flammable gas. Therefore, some people are working out to find out other feasible forms of fuels, whether it is possible to make use of them in the same concept of the fuel cell to produce electricity with a eco-friendly concept. So in that way, methanol, which is CH3OH, and this also contains hydrogen within itself, but it does have carbon and oxygen. Therefore, this methanol can also be used as a fuel cell. If this methanol is used in the fuel cell concept for the same cationic flow and your electronic flow, then you call this fuel cell as direct methanol fuel cell. This third type, phosphoric acid fuel cell, this is also another acidic type of fuel cell where phosphoric acid is used as the electrolyte, which replaces the solid electrolyte membrane. So this solid polymer membrane can be replaced by a liquid form of phosphoric acid, where this phosphoric acid also behaves as an electrolyte to allow the protons to flow through. In that case, this fuel cell is called as phosphoric acid fuel cell. These three types are acidic fuel cells. The fourth one is alkaline membrane fuel cell. Here, alkaline or anionic ions are traveling through the electrolyte. In that case, this is called as alkaline or anionic exchange membrane fuel cell. Then the fifth and the sixth one, which are given in red color, they belong to the high temperature category. They are called molten carbonate fuel cell and solid oxide fuel cell. In the case of molten carbonate fuel cell, the ion which moves in the fuel cell is carbonate ions, CO3 2 minus ions. And in the case of solid oxide fuel cell, it is oxide ions, O2 minus ions. So for the flow of these carbonate and oxide ions, you require a rugged medium, more thermally withstanding and more rugged kind of electrolyte, which could allow these ions to move through. The diffusion of these very strong ions are very difficult, and you require suitable kinetic and conditions that will only allow the ions to move through. So accordingly, you have to operate these MCFC and SOFC at a very high temperature, beyond 500, 750 or 1000 degrees Celsius also they work. But the basic concept remains the same, where the ions are going to move in the electrolyte and the electrons are going to move in the external circuit. The last type of fuel cell is the most interesting one, which is called as a biofuel cell. And there are two types of biofuel cell, microbial fuel cell and enzymatic fuel cell. This is also another type of fuel cell where you make use of any waste waters or solid waste as the fuel. Therefore, I don't have to depend on methanol, I don't have to depend on hydrogen, I don't have to depend on any carbonaceous kind of fuel, particularly gases or liquid medium. I can use any organic waste, solid waste material or effluent that are coming out from the industries as the fuel. That means any waste can be utilized as a fuel in the operation of the biofuel cell. So what is a catalyst that are going to consume these organic waste materials? It is a microbes, the smallest feature of the earth, the microorganisms. Okay, so these microorganisms, basically they are bacteria, fungi, algae, even viruses are also microbial organisms, but the one which are more attractive towards the working of this biofuel cell includes a bacterial kind of microbes. So these bacterial microbes, they act as a catalyst to consume or eat all these bio waste and convert them into useful forms of the energy. Okay, so when microbes are used to do the functioning of the catalyst, then it is called microbial fuel cell. If the microbes are going to be replaced by suitable enzymes, enzymes are also bioorganic materials which can take up the role of the catalyst and consume the organic waste to produce electrons or energy. That is going to be the enzymatic biofuel cell. So these are all the very basic types of fuel cells: acidic fuel cell, alkaline fuel cell, high temperature and low temperature. You can classify the type of fuel cell in terms of temperature, high temperature and low temperature fuel cells. And the last one, biofuel cell, is supposed to be a medium temperature, or you can say it's a room temperature or ambient requirement is simply enough for the biofuel cell to work with. Okay, so having said all these very simple concepts, why these fuel cell technology is not coming for a 100% commercialization? Why not we use this immediately, effectively, for solving our great problems? Particularly, I told you about to reduce the pollution as well as to produce clean energy. Yes, there are some technological issues and challenges that will have to be overcome in order to cross over all these hurdles and then make them really useful in the societal applications. Some of them are given over here. Catalyst. I told you in the first slide, platinum is the best catalyst as far as hydrogen fuel cell is concerned, and this is one of the cost factor. Okay, so when it comes to the fuel cell, there are three important things with respect to the cost. One, the electrolyte membrane. Number two, the platinum catalyst, and number three, the hydrogen. Okay, we will see one after the other. The hydrogen is supposed to be a very risky gas, and the production of hydrogen, the generation of hydrogen from the available sources of materials involves a lot of expenses. Okay, although we know that hydrogen is a very simple molecule or gaseous molecule, the availability of hydrogen in the atmosphere is absolutely zero. It cannot be present also, because it will immediately undergo an exothermic reaction with the available oxygen in the atmosphere. Therefore, we have to generate this hydrogen from some sources. As of now, this hydrogen is coming out as a top gas, low boiling gas in the petroleum refinery. But this hydrogen is very much available in the form of water in the entire earth. But this water will have to be converted into the hydrogen. That means you have to have a very costly process, electrolysis process, to convert or to generate your hydrogen. Once you are producing this hydrogen, then you have to store the hydrogen. Once you are storing the hydrogen, whenever it has to be utilized, you have to transport the hydrogen. So this production of hydrogen, transportation, using, all these involves high risk and cost. You have to very carefully store them without undergoing any explosive reactions. Therefore, this becomes a costly process. Therefore, globally, people are working out to find a suitable alternate for the hydrogen That is why people have gone towards methanol, people have gone towards biofuel cell, where any fuel can be used as a fuel. But the point is, hydrogen is supposed to be the most efficient, high energy, energetically designed material. When you go to the other types of fuel cell, definitely the efficiency, the energy density is going to come down, but still they are working out with the various other forms of the fuels. That is one thing. Number two is a platinum catalyst. Okay, so this oxidation and redox reaction that is taking place in the fuel cell requires the presence of this electrocatalyst, namely the platinum, which is very expensive, all of us know. So there are a lot of activities going on in order to replace this platinum, and also to make use of minimum quantity of platinum as a material which is present only on the surface. That is why a lot of heterogeneous catalyst support and nanotechnology features are coming into play to reduce the amount of platinum that may be required for the working of the fuel cell. That is one aspect. And the third cost is due to the membrane or the electrolyte. This electrolyte membrane, which is put between the anode and the cathode, is a very costly material, because the role of the membrane is very, very important, because the very functioning or the basic working of the fuel cell requires only the ions to flow through the electrolyte membrane. At the same time, when I say membrane, it's a very thin membrane. If there are going to be some defects or cracks or some pores are going to be there on these membrane, what will happen? The hydrogen will come in contact with the oxygen on the other side. If the fuel is going to cross over, when methanol is going to cross over or hydrogen is going to cross over, then you will end up with non-functioning of the fuel cell. Therefore, the functioning of the membrane is very, very vital. It's very critical. It should not. It should be functionally very active to allow the ions to pass through. At the same time, it should be physically present to remove or to not allow the mixing up of the fuel and the oxidant in the actual functioning of the fuel cell. So this becomes very important. Otherwise, the fuel cell is not going to perform at all. Therefore, there are few commercial membranes that are available already in the market. One important membrane is the Nafion membrane. Nafion, N-A-F-I-O-N. So this is the structure of the Nafion polymer membrane. You could see that this contains basically a fluorinated content, carbon F2. This is a Teflon kind of polymer membrane with an extended branch which extends like this. Okay, so there's an ether linkage which is again connected to CF2, O, CF2, and so on. And finally, I have a dangling group of sulfonic acid, this SO3H group. So this sulfonic acid group attached to the main chain of the polymer is making this polymer ionically conductive and allows only the protons or H+ ions or the cations to flow through the membrane. And since the material is basically organic, it is electrically not conducting. Therefore, it will not allow any electrons to pass through. If electrons are going to be flowing through, then the short circuit will happen, and again the fuel cell is not going to work. So it is organic material, organic polymer membrane with a group that is attached to the entire polymer structure, which is called as the sulfonic acid group. This sulfonic acid group is the one which is responsible for the movement of the ions. And this Nafion membrane is the one which separates the hydrogen and oxygen on either side of the fuel cell. So this membrane is very costly. Therefore, a lot of research activities are going on to bring a suitable alternative membrane, which is going to bring down the cost. This DuPont's US DuPont's manufactured Nafion is very costly. It is about $800 to $1,000 per square meter. Therefore, people are working out to reduce the cost. There are two ways in which people are approaching here. One is reducing the cost, but at the same time, we have to be sure that the performance should not also be coming down. And another important point is that this membrane is a fluorinated membrane. See, we are talking about an eco-friendly device, fuel cell, but one of the components that is going to be utilized for the functioning of the fuel cell is the Nafion membrane, which is fluorinated. That means this fluorinated membrane is not an eco-friendly membrane. This is containing fluorine. Therefore, the manufacturing of this Nafion membrane is going to be again a risky process, because you will have the evolution of hazardous hydrofluoric acid and fluorine content materials are going to be utilized for its production. Therefore, this is not appreciated. So therefore, people are working out with non-fluorinated polymer membranes, which can also do the same job of allowing the protons to get conducted because of the available sulfonic acid groups. So therefore, this can be appreciated well by the chemistry people. Therefore, what people are doing is they are looking for aromatic polymer materials like polyether, ether ketone, polystyrenes. All these can be electrophilically, you can attach the sulfonic acid group very easily by electrophilic substitution. The SO3H group goes and attacks, and they are available in the para positions, and these polymer membranes, which are basically hydrocarbons and non-fluorinated membrane, if they possess the sulfonic acid group, yes, they can be made into membranes that can be used as a proton conducting medium in the fuel cell activity. Therefore, a lot of research is going on there also. Therefore, I've tried to impress you on the cost factor in terms of three important features. One, to bring down the cost of the hydrogen. Another point is to bring down the cost of the membrane or the electrolyte that is used for ion transfer. And number three, the platinum catalyst will have to be replaced suitably to bring down the cost. These are three important cost factors. So coming to the challenges, once again, catalyst, expensive platinums are used. They will have to be replaced. Corrosion of the catalyst support. Many times the catalyst supports are used. Nano catalyst supports are used where the platinum is embedded on their surface, so that its requirement or the quantity that is required could be reduced to a large extent to improve the cost, to reduce the cost that is required. Okay, so these corrosion of catalyst support is again a problem that will have to be brought down in order to have an effective and a very good form of the catalyst and support that could be effectively used in the performance of the fuel cell, leading to platinum agglomeration and dissolution. Many of the times what happens, the platinum does not stay there. They get agglomerated, they get dissoluted and go out along with the water. So such things should be avoided. Therefore, a lot of research is going on to immobilize and make the catalyst to be present very much there without getting deactivated for a long period of time, so that it can perform in a durable manner. This is one challenge. The second challenge is membrane itself. As I've already told you, people are going towards non-fluorinated membranes because we wanted to go towards eco-friendly kind of materials that could be used in the fuel cell concept. Therefore, hydrocarbon membranes are being tested very effectively in a very large scale in various research laboratories in the entire world. So here, this membrane, which are non-fluorinated, the basic drawback is that they get degraded very quickly. They get oxidated very easily, they get spoiled very easily, and they cannot be taken for a long use. So the very reason that you are not fluorinating the membrane and the fluorine content is brought down, the capacity in terms of durability is also, stability is also coming down. Therefore, people are moving towards hybrid materials, composite materials, where you can fill the polymer hydrocarbon membrane with the suitable nano fillers and nano incorporation, so that you bring the stability you improve the stability of the polymer membrane. When I say the stability of the polymer membrane, the membrane should be stable in terms of thermal stability, in terms of dimensional stability, in terms of mechanical stability, in terms of performance. Performance also should not be brought down, or should not be coming down. And at the same time, it's a total electrochemical environment, because you have an electrochemical reaction taking place on either side of your membrane, and the stability towards the electrochemical vision or the condition, that is the very much condition of the fuel cell, should also be good enough. Therefore, any membrane which is going to be used as an electrolyte is expected to have good mechanical property, good thermal stability, good performance over a long period of time, good electrochemical stability, good dimensional stability. Sometimes what happens is membrane, because of the sulfonic acid groups, all these membranes, they become hydrophilic in nature, and they swell in the presence of the water, and the water goes and gets absorbed in the membrane, and the membrane becomes flexible, more flexible. The stability is lost. And this dimensional stability, if it is going to be lost, the bonding effect is going to be lost, and again the transfer of protons is going to be affected. Therefore, you should not have a dimensional stability problem also. So people are looking out to improve all these various types of stability and the characteristics that a membrane will have to be possessing when it is going to be used in the fuel cell arrangement. The third challenge is about the hydrogen, which again I told you very well. The generation, cost, safety, all these are playing a great role, and people are working out to address all these issues that are associated with the hydrogen. Now, now let us move on slowly to the main topic of my today's talk, which is nothing but the microbial fuel cell. So these microbial fuel cells, I told you, microbes are used as a catalyst. Therefore, I'm reducing the cost by replacing the platinum with the microbes, number one. Number two, I'm not using hydrogen. Hydrogen is very costly. Therefore, I'm reducing the cost of the working of the fuel cell by not utilizing the hydrogen and making use of the waste. Okay, I'm not taking.
Dear ma'am, a
Yes,
slide
ma'am.
is not visible, ma'am. We are having the challenges ahead with fuel cell technology slide only, ma'am.
அதுதான் பேசிட்டு இருக்கேன். I'm talking that.
Microbial fuel cell. Okay, ma'am.
MFC, அதுதான் பேசிட்டு இருக்கேன்.
Yes, ma'am. Yes, ma'am.
Okay. So when it comes to MFC, I told you hydrogen is replaced by waste fuels. Therefore, the cost is reduced there. Platinum is replaced by microbes. The cost is reduced there. And in our laboratory, we are working out with various types of non-fluorinated polymer membranes, which are hydrocarbon-based membranes. Therefore, we are trying to bring down the cost there also. In that way, more cost-effective microbial fuel cell when compared to the normal fuel cell is being utilized. In addition to that, we are also converting the waste form of energy to usable form of energy. So that's a simultaneous advantage. So the challenges that are associated with this microbial fuel cell, although it has got various advantages, what I have listed is membrane biofouling. This is a major problem because I'm using wastewater. A lot of microorganisms and other features are going to be there, and these membranes, they get fouled over a period of time. Therefore, the activity, the efficiency of the membrane comes down. Therefore, people are working out to improve or retain the proton exchange capacity of the membrane by not allowing the membrane to get fouled over a period of time. This is one feature. The second feature is that there is something called oxygen permeability. This we will discuss later. In the few slides, these membranes should not be oxygen permeating. If they are going to allow the oxygen, there is a trouble in the functioning of the fuel cell. Therefore, a lot of work is going on in that area. Number three is substrate crossover. This substrate crossover is something very similar to hydrogen getting crossed over. Okay, if the waste is not utilized as food by the organisms and they simply cross over and reach the cathode, then the reaction that is expected to happen is not going to be fulfilled and the electricity is not going to be produced to the extent what we require in the fuel cell. Therefore, that is also another challenging area. And most important challenges with respect to microbial fuel cell is the upscaling and the durability. Okay, I can do this in the laboratory scale. I can perform an experiment in the lab and I can make a very small MFC device and then I can prove, see, the COD content has reduced, the BOD content has reduced, the oxygen content has improved, the waste is reduced, the energy is produced, I'm able to get a better form of the water, the purity of the water is very much improved. All these things I can prove, but this is being done in a prototype and a small scale arrangement. When it comes to the commercial value, when it has to gain the commercial value, it has to be taken to large scale, upscaling. The upscaling becomes a real challenge, and the durability of the material. Okay, I'm proving that this much power density is produced in the laboratory, but how long this power density is produced, how long the membrane is able to allow the protons, how long the conductivity of the material is retained, maintained. So these are all the areas where people are concentrating in research. Okay, those who are interested in research, they can catch hold of these things. If you're really wanting to do something with respect to this fuel cell development, these are all the areas where you can concentrate and do something to bring out the research activities. So how these research challenges can be addressed? There are various approaches. What we are doing in our laboratory is being included in this table. Platinum catalysts are replaced by nano-sized particles. Nanotechnology is being utilized there, and alternate non-noble metals can be used if it is a case of alkaline membrane fuel cell. And microbial fuel cell is another answer for substituting the platinum catalyst. Similarly, nanofibers, nanotubes, graphenes, nanocomposite membranes, all these are different approaches. You can work it out to bring a solution for the existing limitations and challenges. Now we'll move on to the working of the microbial fuel cell. Now we all have understood the working of the simple fuel cell. Okay, so hydrogen is supplied, oxygen is supplied, ions are passing through, electricity is produced in the external circuit. Very similar kind of reaction is taking place in MFC also, but I am not using hydrogen. I'm not using platinum. I'm not using Nafion very costly membrane. Therefore, I'm reducing the cost in all these ways. Okay, a little bit of background. In the late 1700s, Luigi Galvani, who is supposed to be an Italian anatomist, noted that a detached frog's leg twitched in response to the electrical charges. This particular finding has evolved the field of electrochemistry. And in the year 1911, Porter, he was the first scientist to publish a paper on electricity generation using bacterial microorganism. And today, this microbial fuel cell have become the potential solution not only to provide a clean and renewable source of energy, but also to reduce the bio wastes. So how does this work? We will see in the next slide. So microbial fuel cell is supposed to be the best answer which can help in converting the bio waste into electricity. Okay, this particular slide, I've just given the different types of fuel cell and different anodic and cathodic reactions that are taking place. Okay, so what happens in the first case is the alkaline membrane, AEMFC, or alkaline fuel cell, AFC. It works at a temperature of about 60 to 90 degrees Celsius. Here, hydrogen is supplied in the anode, oxygen is supplied in the cathode. Hydrogen combines with the hydroxide ions to give you water and electrons, and these electrons take up the external circuit to reach the cathode and combines with your oxygen supplied there and the water to give you hydroxide ions. So these hydroxide ions are always produced in your, negative ions are produced in your cathode, and they go to the anode through the electrolyte membrane. And if it is the acidic fuel cell, it is a proton that get transferred. In the case of acidic fuel cell, PMFC, hydrogen splits into H plus and electron. This is the one which you have seen in the first slide. And oxygen combines with the moved electrons and the moved protons to give you water. Okay, so the net reaction of the first and the second is one and the same, but the ion movement is different. The ions are different. The produced ions are different. Okay, so depending on whether it is acidic or alkaline kind of fuel cell. And in the case of direct methanol fuel cell, I told you that hydrogen is being replaced with the methanol. Because methanol is used as a fuel, in addition to the electrons and protons, you have the CO2 is also being produced. So this is one added thing in addition to your hydrogen. If it is a pure hydrogen, you don't have CO2 at all. Because it is containing carbon also, you have a small amount of your CO2 that is being produced. But the entire basic concept remains the same. Movement of electrons and protons. And the fourth one is your phosphoric acid fuel cell. Here it is the same as that of your PEM fuel cell. The only change is here I make use of an electrolyte membrane, and in this case it is the electrolyte solution, which is nothing but your phosphoric acid. But both the solution and the electrolyte medium, solid medium, does the same job of allowing the protons. And when it comes to the high temperature fuel cell, which operates at about 650 and 1000 degrees Celsius, as in the case of molten carbonate and solid oxide fuel cell, carbonate ions, they are consumed in the anode, they are produced here because they are negative ions. And similarly, if you are making use of oxide ions, it is consumed here and produced here. Okay, so in these examples, I have tried to show you the use of hydrogen. So in these high temperature fuel cell, you don't have to depend on hydrogen. You can also depend on other carbonaceous fuels, but a slightly different type of reaction is going to take place. Although the basic formation of your electrons and ion formation are going to remain the same. Okay. Now we'll move on to the last one, the topic of today's talk, biofuel cell. This works at a room temperature, at ambient condition. Therefore, I'm not going to increase the temperature. Generally, any chemical reaction, when you try to increase the temperature, the activity increases. The diffusion capacity of the ions and all the rate of reaction increases. So that's not required in your biofuel cell because it works only at room temperature, and that is not required is one point, and that should not be increased is another point, because these organisms, these enzymes are basically bio components, and they get denatured when they are taken out of their pH value, out of their temperature, out of their pressures. They may not exist there, they may get denatured. Therefore, you have to maintain the same condition, their living condition. That's nothing but the ambient condition. So here a simple glucose molecule you could see here combines with your water to give you carbon dioxide, 24 protons. So in one single reaction, instead of 2 protons that are being utilized in the all other cases, in this case, here I have 24 protons coming out from one molecule of the glucose. It's a hydrocarbon molecule. Okay, so electrons are being produced, 24 electrons, and of course, you have the oxidation and you have the reduction process. So how this is taking place, I'm not depending on platinum. It is a microorganisms that microorganisms or the enzymes that eat the food, that eat the glucose molecule, that take up this as a food and produce the CO2, H plus and electrons. Immediately, if I have a path for the movement of these protons, which is nothing but your polymer membrane, then immediately they get transferred and the electrons are going to take up the electrical route. And therefore, the electricity is going to be produced in biofuel cell also. Okay, so then such a simple concept, how does it work? And what is it I have to do to make it work? We will understand that with this particular slide. Okay, so MFC is a bioelectrochemical fuel cell. Now I call this as a bioelectrochemical. Earlier things I said it's electrochemical. Because I'm using a biomaterial, it is bioelectrochemical fuel cell, where the anode reaction is controlled by the microorganisms and not by the catalyst. And anode respiratory bacteria are the one which are playing the major role of converting the bio-waste materials to the electrons. So how it is happening? Look at this diagram. This is very similar to the previous one. But here, instead of hydrogen, I'm supplying the fuel. And these fuels are going to be eaten by the microorganisms that are present over here in the anodic chamber. They consume, oxidize the fuel, and the waste goes out. And during the oxidation, ions and electrons are produced. Ions, they necessarily take up the route of the proton exchange membrane to reach the cathode, and the electrons take up an external circuit. And here you have the oxidant combining with that, and the reduced oxidant is going to come down. So what is the only difference? The bacteria present in the anode chamber that are attached to the electrode, that is your anode electrode, is free of oxygen. That means you have to maintain an anaerobic condition without the presence of the oxygen for the organisms to live there and consume the food and generate the electrons. Suppose I have an oxygen that is present there in the anaerobic condition, immediately the oxygen will consume and your reduction process will also take place there itself, and therefore there are no more separation of the electrons and protons. Therefore, to avoid that reduction, you have to maintain an anaerobic condition. Anaerobic condition is a condition where you have absence of oxygen. Okay, if I don't have the presence of the oxygen here in the anode, the foods are forcibly consumed by the anaerobically living organisms and then generate the electrons and protons. If this condition is maintained, the bacteria consume the waste and transfers the electrons to the electrode. Cathode chamber is exposed to the, whereas the cathodic chamber, right side chamber, cathodic chamber will have to be exposed to the oxidant. Here oxygen is the oxidant and they undergo the reduction process and the electrons are consumed there. Thus the electrons, oxygen, protons combine with each other to form the electricity and the water as the byproduct. Okay, so what we try to understand is just by making the anodic condition and anaerobic as an anaerobic chamber, not allowing the oxygen to be available there, the electrons are forced to take the electrical circuit and the protons are forced to move through the electrolyte membrane to reach the cathode, and all of them they get combined with each other to produce water, and this makes the flow of electrons, which is nothing but the electricity that is going to be produced. So if I maintain the anode as an anaerobic chamber, yes, I can generate electricity from bio waste. And what is the catalyst that is being used? It is the simple microbial bacteria. Where are these microbial bacteria coming from? I am not going to explicitly add them. I'm not going to deliberately add them. I'm not going to produce them in the laboratory. Whatever microorganisms, bacteria are available in the wastewater itself is sufficient to consume and produce the energy. Only thing is, I am not allowing the oxygen to be available there in the anode. In the absence of oxygen, it is forced to eat and produce the electrons, and the electrons are going to take up the electrical circuit. This is the only thing which I'm going to do to convert the basic fuel cell into a microbial fuel cell. That's it. So hydrogen is not there, platinum is not there, and the membrane, of course, right now Nafion is a membrane that is being utilized by so many people who are working in this microbial fuel cell. But in our laboratory, we have found a solution for replacing this Nafion membrane also, and we are working towards reducing the cost of the microbial fuel cell by making these hydrocarbon membranes to be very effectively working in the microbial fuel cell. Okay, so what are all the different factors How do the microbial fuel cells performance can be judged? They can be judged based on various parameters. More importantly, microbial inoculum. What kind of inoculum is present? If I'm making use of a textile industry effluent, the textile industrial effluent will contain some aromatic compounds, benzene-based compounds, some toxic materials could be there. If it is from a tanning industry, leather industry, it may contain some toxic elements, lead, vanadium, chromium. All these are toxic metals. Okay, they could be present. If it is a milk industry effluent, I can see a lot of organic contents as the waste material. If it is a brewery industry, it is different. If it is a restaurant or a hotel or a domestic effluent, the contents are different in different kinds of wastewaters that are being produced in various activities. Okay, but the organisms which are able to live in the toxic condition, which are able to live and consume the food in the dairy industry or textile industry, that itself is sufficient for them to be put into the arrangement of the microbial fuel cell so that they utilize the food, because they will not die, because already they are existing in that particular environment, and that environment is brought to the anaerobic condition in the MFC. That's the only change I'm doing it. Okay, so the kind of microbial inoculum, what kind of species are there, whether they are gram positive or gram negative bacteria, whether they are able to immediately transfer the electron to the electrodes, or they take time, or they require a mediator to transfer the electrons. All these are based on the different types of microbial inoculum, which determines the performance of the MFC, and the chemical substrate, what kind of food is available for the microorganism, and the type of polymer electrolyte membrane. This polymer electrolyte membrane, whether it is good, whether it is fouling extensively, whether it is good in terms of anti-fouling effect, whether it is ionically conducting, proton conducting, or anionic conducting, the type and the condition and the characteristic of the polymer electrolyte membrane, which is used as an electrolyte there in the setup, is going to also determine the performance. Then the internal and external resistances. Always, whenever there is a flow of electrons, whenever there is a movement of ions, whenever there is a reaction taking place, there is always a resistance happening. There are various types of resistances. So how do you overcome these resistances? How do you reduce these resistances also matters to improve the performance of the microbial fuel cell. And then the electrode material. These electrode material, generally they are electrically conductive material that are used because they have to capture and allow the electrons to flow through them. Therefore, I have to make use of a metallic or an electrode material which are conducting in nature. And the spacing between the electrodes, all these determines the overall performance and the power generation that can happen from the microbial fuel cell. So here you can see the incoming fuel wastewater and the outgoing carbon dioxide, and similarly incoming oxygen and outgoing water. Here is the anode electrode and here is the cathode electrode. The microorganisms are sitting over there, and they eat the food, produce the electrons. The electrons immediately jump into the external circuit. Protons go through the polymer electrolyte membrane and reach the cathode. So you can make use of municipal wastewater, agricultural wastewater, industrial, dairy, brewery, food. You can think of any wastages. Okay, so you can make this entire process to work out. And similarly, you can have various types of oxidants. You don't always have to depend on oxygen. It could be any other kinds of these oxidants can also be used. Depending on the case, maybe you can also reduce. For example, groundwater nitrate content, if you want to reduce, yes, it is possible to make use of the microbial fuel cell to denitrify, for accepting the denitrification to happen and then produce nitrogen. And these things are produced, these things are happening in addition to the electricity, which is the bioelectricity that is produced in the system. Okay. So what is the role of the membrane? The ideal membrane that is used in the MFC should inhibit the transfer of substrate. It should not allow the food to cross over, and it should not allow the oxygen. Food should not get transferred from anode to cathode, fuel, and oxygen should not get transferred from the cathode to the anode. And it should only allow the respective ions to pass through efficiently and preferably with a low cost. There are various types of membranes: cationic exchange membrane, anionic exchange membrane, bipolar membranes. There are bipolar membranes which has got two forms. One is cationic and another one anionic. How they are used, we will see some slides later. Okay, then there are some porous membranes are also being used, separators, ceramic separators, these are also being tried and a lot of research is going on. But the basic role of this microbes in the fuel cell is the microbes, they grow in the anodic chamber, metabolize the carbon substrate, for example, glucose, to produce the energy. That is a basic job. And the basic job of the membrane is, it should, the major role is to permit the ions to flow through, and it should not allow the mix-up of the reactants, and it should physically separate the two electrodes, anode and the cathode. These are the main functions of the membrane electrolyte. And I have told you the most commonly used membrane is Nafion. It is produced by DuPont, but when it comes to Nafion, when it comes to microbial fuel cell, the Nafion is a complete failure. Why it is a failure? Because of several limitations. Number one is cost. Of course, we know already the cost is a big factor with respect to Nafion. But when it is the MFC, it is oxygen leakage. So what happens is Nafion is permeating or allowing the oxygen to diffuse through it and reach the anode. So when this oxygen is going to cross over from the anode to the cathode, the anaerobic condition maintained or required for the microorganisms to grow over there and do its functioning is going to be bothered, it's going to be damaged. So this oxygen crossover is a great problem with respect to the Nafion, and therefore a lot of other membranes which is not allowing the oxygen to cross over, which is not allowing the substrates to cross over, are gaining more importance in the research angle. And then the substrate crossover and the accumulation. Okay, this accumulation is nothing but the protons without getting transferred. If it is biofouled, if the crossover of oxygen is too heavy, then the protons are not able to transfer, which is otherwise are expected to happen in the efficient working of the fuel cell. Okay, so what happens? The protons, they get accumulated in your anode, and they make the entire situation more and more acidic because of the presence of the H+ ions, because they are not transferred to the cathode, and the condition is not conducive enough for the organisms to grow and do its functioning of consuming the food and producing the electrons. Therefore, it becomes a complete failure when Nafion membrane is used. So intensive research is going on to find out a suitable membrane to overcome all these problems with our with respect to the Nafion. Nafion structure, I think we have seen in the previous slide. They've got a hydrophobic and a philic kind of situation. The hydrophobic is your fluorine background, and wherever you have this SO3 minus H plus labile group that is dangling in the entire polymer structure, or the hydrophilic region, and these philic regions which contains the sulfonic acid group are the one which is responsible for the transfer of the protons to take place through them. Therefore, the ideal membrane is expected to have a good ionic conductivity, a good stability, chemical stability, long-term for long-term use, and good stability in electrochemical operating condition of the fuel cell. Very low fuel crossover is to be required by the membrane. Good mechanical properties, resistance to swelling. Too much swelling should not happen because they are all basically hydrophilic in nature. They absorb a lot of water and their stability goes up. That should not happen. They should not too much be absorbing the water, and they should be readily available with reasonably low cost. So this particular slide is trying to give you, these are all the different membranes that we have prepared in our laboratory, which is nothing but your sulfonated polyether ether ketone and some composite membranes like sulfonated polyether ether ketone with sulfonated silica, sulfonated titania, functionalized graphene oxide, polyetheramides. These are the various compositions. Okay, so what we have tried to do right from 2011, I think some of the applications are given over here. All these membranes have been done only with respect to the microbial fuel cell. I have not taken the other fuel cell types. So what is it we are trying to do here is to improve the property or the performance of the membrane in the microbial fuel cell, because you wanted to improve the stability, you wanted to improve the functional character, you wanted to have a more durable form of membrane, you wanted to have a composite material which is more stable. So in order to address all these things, we started working out with different types of membranes, and we have recorded power density. The values are given over here, and the respective journals are also given over here. Okay, so we were able to go as high as 1,000 and odd milliwatt per meter. So one important drawback of microbial fuel cell is that when you are going to make use of hydrogen in the normal fuel cell, the amount of power that is going to be generated is very, very high. Okay, but in the case of microbial fuel cells, since I'm not depending on high energy effective hydrogen, it's a waste material that is being consumed for electricity generation. The power produced is very low. Okay, so this is about 1000 and odd milliwatts per meter square. That means the power generated is not so much when compared to the hydrogen based fuel cell. Okay, now to look into some of the interesting features and the ways in which this microbial fuel cell could be an answer for a number of existing problems in the entire world. How and what are all the ways in which these microbial fuel cell can be looked upon? This will also give you some idea where you can begin your research activities. For example, the ways in which MFC can improve the world could include a brewery, domestic wastewater treatment, it could be a desalination, it could be even hydrogen production. Okay, so this is really interesting. Hydrogen production can also be done by making use of microbial fuel cell and biosensor. All these things we will see one after the other. Okay, brewery wastewater. This is a hotel-based wastewater that may be coming out. So this food manufacturing wastewater, they are good in terms of organic content because they are coming from the food industry. They are very rich in organic content. They become really an ideal fuel which is present in the wastewater, and their composition is supposed to be more constant and more efficient because it's a regular water. Every day they work and then it's being let out. Okay, so this is one practical example in your Australia, a beer company. They partnered with the University of Queensland and they developed this microbial fuel cell. And you could see that there are 12 long tubes. At the top, they feed the wastewater, and at the bottom, better water is coming out. And the produced electricity is utilized by the same hotel for their different applications. Okay, so that's what is the example given over here. And coming to the sewage treatment, yes, sewage treatment, sewage water. They can also be used as a fuel in the microbial fuel cell. Here, the change is the amount of organic material that could be contained in the sewage is not uniform, not consistent, as we have seen in the brewery industry. It could be varying depending on the location and everything. Okay, so these organic waste material, yes, it is possible to convert them into useful forms of energy, provided you are able to remove the toxins. You are able to remove the non-biodegradable condition, which may be a preliminary step that may be required to make use of such sewage water for your MFC system. This is what we are doing in our laboratory. We are making use of ananovosity sewage water, pre-treated, preliminary treated, and then we produce electricity. And of course, these additional requirement, extensive treatment can be justified by the fact that we are producing electricity in the entire process and trying to dump fewer pollutants into our water bodies. Yes, MFC can also be used as a desalination unit. Desalination, all of us know, salt water is very much available everywhere. And if this MFC could be slightly modified by making use of two semi-permeable membranes, look at this particular diagram. This is a salt water entering into the system. On one side, there is a semi-permeable membrane which allows only the anions to pass through. That means this is an anion exchange membrane, and on the other side I have a cation exchange membrane, and this chloride ions and sodium ions are correspondingly removed by these semi-permeable membranes on either side. And this is a third chamber. I'm just introducing a third chamber where this separation is taking place in addition to the original anode and cathode. So this, in your original anode, the electrode is available where the bacteria are growing, and they produce the electrons. Okay, so the produced protons, instead of passing through the electrolyte, they combine with the chloride ions and they form the hydrochloric acid on the left side. Similarly, on the right side, if you are allowing the Na plus ions, already your OH minus ion will be there and they combine to form the alkali. So in this way, simply by introducing a third chamber and allowing the water to flow through and making the semi-permeable membranes to be available on either side, it is possible to remove the salt and make the water more purer. Simultaneously, you are also producing the byproducts of acid and alkali on either side of your chambers. So this is a conventional type of desalination that could be converted into the MFC desalination, which is a useful product. This is really interesting. Hydrogen production can also happen in your microbial fuel cell. We all know that in the first slide, in the principal slide, I explained to you that just by maintaining an anaerobic condition in the anodic chamber, you can make the fuel cell to make electricity. Suppose I'm making the cathode chamber also anaerobically saved. Okay, so what happens if the oxygen is not supplied in the cathodic chamber? Okay, so basically in anaerobic chamber, the protons and electrons are developed, and these electrons go through the external circuit to reach the cathode, and the protons reach the cathode through the electrolyte. And when there is a presence of oxygen, they get combined and then form the water. If there is no oxygen present on the cathode chamber also, then the protons and electrons recombine to form the original hydrogen. Okay, so just by introducing, just by having the cathodic chamber maintained in an anaerobic condition, already anode is anaerobic and cathode is also maintained anaerobic, you are not allowing oxygen on both the sides. Yes, it is possible to split and make them combine to form the simple hydrogen. So in this way, I'm making hydrogen, which is supposed to be a very costly process by the conventional routes. So the standard MFC is converted to hydrogen production just by keeping both the chambers anaerobic, and of course a small amount of initial electricity that may be required to begin with the process. This is the most efficient and environmentally friendly way to generate hydrogen. Otherwise, all other conventional methods of producing electricity or producing hydrogen is a very costly method and non-eco-friendly method too. So this becomes a real advantage. Yes, MFCs can also be used as a sensor. Microbial fuel cells, they run at low power sensors. For example, there's a remote area, there's a soil available, and at the top you have the water. Okay, so in the top you are supposed to have an aerobic water. This could be an ocean or a sea. Okay, you have the sand or the mud at the bottom. You have a region, you place an electrode over here and an electrode at the top, your anode and cathode, and just simply have a connecting wire between them, electrically conducting wire. Okay, so what happens, these bacteria, they produce the electrons and they take the route of moving from anode to the cathode, and simply by having a capacitor over here, you can charge the capacitor and you can have the source of energy to run the remote sensor. The sensor could be, it could sense some features or some BOD or COD parameters or oxygen parameters or the temperature. It could be any kind of sensor that could be put over there, which requires a source of energy that can be derived from the setup of this MFC over here. Okay, so this simple arrangement is very healthy, and it is very advantageous and simple also, because you don't have to replace the bacteria. The one which is already there in the system is going to take care of all these things, and it's going to perform its role in a remote way. You don't require any interventions in between, because they can source their energy by themselves, and they are self-sufficient, and they can be sustainably there for a long period of time to get them operated. So such kinds of applications are also looked upon. Then cleansing polluted lakes and rivers. Yes, there are a lot of organic waste and chemicals when they are thrown out into the water bodies. Simply you have an anaerobic electrode at the bottom and you have an aerobic electrode at the top. You have a connection, and it's possible to convert all the organic pollutants into different other forms of volatile gases and other things. By doing so, you are reducing the entire polluting components that are otherwise present in the wastewater bodies. Okay, this is a very simple arrangement. This is seen in an African country. They make a very simple homemade microbial fuel cell to recharge their cell phones. Okay, so there's a very small amount of energy that could be produced to recharge their cell phones. What is it they are doing? This Lebon group in Africa, they simply take the soil, mud, manure are put over there, and copper wires, bucket, and a graphite cloth. Only this much is the simplest requirement to make a very simple MFC device. Okay, so you have the bucket, you have the mud and the water, and you have an electrode at the bottom, and the wire is getting connected to the top, where you have the oxygen level presence over there, and the graphite cloth is going to make it's going to be your electrode, where the electrons are going to reach them. And this is a very simple arrangement, and you can charge the cell phones by making use of a very simple normal components that may be easily available. Okay, I think I've taken a long time for getting into the real research level. Any doubts till now? This particular part, another 10 to 15 minutes, I'll be talking about the real research activities. Okay.
Any doubts from the participant side regarding the session?
Okay, we will have some time at the end, right? Okay, I will quickly sweep through next 10 to 15 slides where till now I have explained you the overview of the fuel cell, overview of the activities and challenges, and what is the major idea that is going on globally, and the scope also I have explained you to some extent. Now, what is the scope, what is the challenge, how it is addressed at the research level. Okay, so as I've already mentioned several times, there are two important activities that are going on in the microbial fuel cell. One is for the entire overall performance of the fuel cell, you require two important transfer activities or mechanisms that are going on. One, the bacterial electron transfer. Whatever electron is going to be produced should be transferred to the conducting circuit. Number two, ion transfer. Whatever ions are going to be produced should move through the polymer electrolyte membrane. Okay, so if you are activating, if you are seeing to it that these two activities are effectively going on, that's the thing which is required for you to produce the electricity from the bio waste. So how do we improve this is the fact or the real research challenge that people have undergone, and people are also undergoing right now, and in future also you are expected to improve this performance. One is your direct electron transfer. Electron transfer is of two types. One is direct electron transfer, the other one is mediated transfer. In the case of direct electron transfer, there are certain microorganisms which are basically gram-negative bacteria. First, we should try to understand the difference between gram-positive and gram-negative. There are gram-positive bacteria and gram-negative bacteria. These gram-positive bacteria, they have a very thick peptide, like a lipid layer, which does not allow the electrons to immediately get transferred to the electrode. Okay, so the gram-negative bacteria, they don't have such thick layers, and whenever these microorganisms they produce the protons and electrons, these electrons get shifted immediately without any hurdles, because they have some nanowires and nano features which make them to allow the electrons to transfer easily. In that case, you don't require mediators. Okay, but in other cases, some cases they require mediators, because these mediators, they act as both reductant and oxidant to carry and to leave the electron into the electrode. Okay, so what is appreciated is if the microorganisms are gram-negative and they are able to perform without a mediator and transfer the electron, that is the best condition that may be required for the transfer of electrons. And similarly, coming to the electrolyte mechanism, where the protons are going to be transferred. These protons, basically I tried to explain the structure of the Nafion in the previous slide. There is a sulfonic acid group that is present in the membrane. This sulfonic acid group is the one which is present throughout the polymer membrane, and this H+ ion is the one which is mobile, which is labile, and allows more and more transfer of protons to get jumped from one acid group to the other acid group. So this movement of, whenever there is a production of protons in the anode, they move from one sulfonic acid group, one chemical group to the other chemical group by the hopping mechanism or jumping mechanism. The proton get jumped from one acid group to the other acid group. By doing so, they reach the cathode. Okay, so this mechanism is called proton mechanism or hopping mechanism. This is also called as Grothus mechanism. Okay, so proton hopping mechanism. The other mechanism in which the protons can be carried over from anode to cathode through the electrolyte membrane is that the presence of water. Okay, so these membranes, I told you, they are hydrophilic in nature. Because of the very presence of the sulfonic acid group, they absorb the water. And where are these water coming from? In microbial fuel cell, it is aqueous environment. You always have water. If it is other types of fuel cell, water is being produced as a byproduct, and therefore always water is available. And these water, they go and attach themselves to these polymer membranes because they are hydrophilic in nature. They attract the water and swell make the membrane swell. And this very presence of the water becomes a medium or a carrier for the protons to get transported from the anode to the cathode. So this mechanism is called vehicular mechanism. Therefore, if I have a good membrane, I can call it as an electrolyte membrane, a good membrane, when the proton hopping mechanism is supported because of the presence of the sulfonic acid groups or any other suitable groups that may allow the protons to get transferred. Number two, it should be slightly hydrophilic, and it should not be too much hydrophilic. If it is too much hydrophilic and too much swelling, the stability will be going on. Dimension stability will go off, and that will give you bonding trouble, and when the bonding will be loosened and other problems will be created. Therefore, to a sufficient adequate level, the hydrophilic nature should be maintained, and this water presence is going to make the vehicular transport also to take place. Therefore, at a large water what I try to make you understand is both electron transfer and ion transfer mechanism should be efficiently facilitated by making use of the MFC system. When it comes to electron transfer, it is a role of the microbes. The microbes should be able to immediately transfer the electrons to the electrodes. When it comes to the ion transfer, it is a performance of the membrane. The membrane should not only allow the hopping mechanism or the chemical exchange route to take place effectively, but also should be hydrophilic in nature to some extent to allow the water to make itself as a carrier to transport the protons. If this is happening, or if you are trying to improve these conditions, you are making a better and better MFC. In that angle, we started working out in our laboratory. For the past 1 decade, we have been working in microbial fuel cell. We have come out with very good membranes. The earlier point is we wanted to go always towards a hydrocarbon material, eco-friendly material, non-fluorinated, non-Nafion based membranes. Okay, so these membranes have been developed over a long period of time, and the capacity of the membrane, not only in terms of functional capacity for conductivity, but also in terms of durability and other factors that may be required for the functioning of the fuel cell, we try to improve the conditions by making them a composite membrane, hybrid membrane, blend membrane. So many combinations we have worked out. The 3 examples I'm trying to give you in this talk. One is your POS, polyhedral oligomeric siloxane, which is a nano caged material. When this material is sulfonated, there are 2 ways in which these fillers are used. One is directly you can make use of them as a filler. The second one is you can functionalize a filler so that you are still improving the functional character as well as the proton carrying supporting activity by the filler also. But therefore, what we try to do is the polymer membrane itself is conducting, and the incorporating material, nano fillers, nano features, they are also conducting in nature, and therefore the conductivity and the performance can be improved. In that way, we try to develop this SPOS, sulfonated polyether ether ketone membranes, and we identified our Anna University sewage water and the initial COD. This reduction in COD always tells you the water is becoming purer and purer. Okay, this is an indication of impurity of the water, COD and BOD values. So this was tried in our group, and several basic characterization methods. I thought of spending more time here, but okay. So these are all the FTIR methods which confirms the functionality of the polymer membranes that are developed, functionality of the nanofillers, and these are all your composite materials. This is your POS, sulfonated POS, and this is SEM images of the caged structured POS materials. And after sulfonation, how do they appear? And these are all the SEM photographs of the membranes, and these are all the characterizations which confirms the presence of your sulfur, your silicon, your POS content, and everything. And finally, we arrived at, we also did some XRD to compare the crystallinity and reduction in crystallinity property and hydrophilic nature, and ion exchange capacity. This ion exchange capacity, your water uptake capacity, resistance, conductivity of the membrane, and the oxygen mass transfer is another very important parameter. I told you at the beginning, the transfer of oxygen should be reduced in order to improve the anaerobic conditions so that the electrons are heavily transferred into the electrical circuit, which increases the output current. And the maximum output what we have obtained using these membranes is 162 milliwatts per meter square. Okay, and we always try to compare this with the the base membrane as well as the Nafion membrane in the laboratory. These are all the polarization curves which tells you the power that is generated. So this is with SPOS. And finally, we arrived at a conclusion that most of the organisms that were present in the system were gram-negative, and that is why the electricity were able to be generated. This is a phylogenetic study, a bio study that is done to identify the different organisms along with their classification. And this is another second concept. In the similar line, we tried with the sulfonated titania nanotubes, and these also gave some good results. Very similar kind of work was done, and we were able to go with a 121 milliwatts per meter square. And we started doing with various nanofillers, and recently we started doing with anti-fouling agents. Okay, why this anti-fouling agent is important? Because these power density are giving very good values when we perform these experiments for 2 to 3 weeks. And beyond 3 weeks, if we continue to make use of the same setup, the membrane loses its property because of fouling, because of the bioorganism fouling, which has formed as a thick layer on the membrane and does not allow the protons to move through. So that becomes a problem. Therefore, what we try to do is we started adding some anti-fouling agent. Silver is one of the best anti-fouling agent in order to prevent the adherence of the microbes on the membrane, and we tried evaluating such membranes. Okay, then we arrived at a situation where after 3 weeks it was 60 plus or minus 3 milliwatts per meter square, but after 3 months we were able to see that the performance increased because of the silver content. But at the same time, we should remember the silver will also go and kill the microorganisms that may be present otherwise in the anodic chamber. You have to make sure that the silver is not leached out of the membrane. At the same time, it is present in the membrane to avoid more of these organisms to get attached to the surface of the membrane, so that over a long period of time it is able to perform. So we were able to get some good promising results, and all these have been published. These are some of the facilities which we have. We do have a hydrogen oxygen fuel cell setup, and some of the electrospinning and these facilities are available. These are some of the developed MFC structures. There are dual chamber, single chamber, tubular model, various fabrications have been obtained. So this is one of the best, these are all best membranes where we achieved as high as 1345 milliwatts per meter square. Some of the recent publications. And in this area of fuel cell, we have also been granted with 3 patents. One is with respect to the development of membrane. Second one is membrane for MFC, and the third one is with regard to the design of the fuel cell. And I have to acknowledge various funding agencies that have donated us enormously to do a lot of activities with respect to the fuel cell. And the one which is presently going on in our lab is a STARS project. And as a concluding remark, I would like to conclude that microbial fuel cell is a very promising technology for water sanitation coupled with bioelectricity generation. 2 important mechanisms that will have to be looked upon and improved is electron release transfer acceptance mechanism and the ionic release transfer acceptance mechanism. Investigations on oxidation of organic substrates by the exoelectrogens, or those electrons which are able to produce electrons. In the anaerobic anode, anti-biofouling characteristics of PEM is important, along with high ionic conductivity without sacrificing the conductivity property. With appropriate MFC design for a more durable and scalable functioning towards efficient power production is the current research that is going on in this area. Scope of the work for improvement. One of the greatest advantages, direct conversion of organic waste materials into electricity. You are expected to have a very sustainable system in the near future by making use of wastewater for energy production. It could be from bioremediation of organic pollutants, a pharmaceutical industry, petrochemical, dye industry, agro industry, anything, any industrial waste could be used as the fuel in the MFC setup. A better research can definitely speed up these processes, and really we expect that the fuel cell is going to power the society, and it's not too far. Just to have an interesting point, this is my last but one slide. Let me see any of the participants are able to answer these questions. MFC can be converted into a desalination unit by? Can anyone answer this?
By 3 membranes, ma'am. Instead of the 2.
Yes, by introducing the third chamber. Very good. Proton conductivity of the standard electrolyte for use in fuel cell is in the range of, can anyone remember? Slide apart the governor.
5, ma'am.
By? Someone said something? Okay, I will give you the answer. It is around 10 power minus 2 to minus 1 Siemens per centimeter. Okay, that's the range of conductivity that is required for a membrane to be used as an electrolyte in fuel cell. Third question, somebody can answer. By maintaining the anaerobic condition in the cathodic chamber, MFC can be used for?
Water purification, ma'am.
No. By maintaining anaerobic condition in the cathode.
Generating electricity.
Generating, not electricity. Electricity is always generated. I very much stressed on this point. Yes?
Desalination.
Yeah, somebody said hydrogen generation. Very good. Hydrogen can be generated. Okay, if I'm not having oxygen, the cathode. Commercially available fluorinated membrane that do not perform well in MFC is. Can someone name the membrane? Yeah, that's correct. Nafion. Why Nafion is not performing in MFC? Your voice is very meager. I think you are right. Oxygen diffusion is very high.
Substrate crossover, ma'am. Substrate crossover and accumulation.
Yes, exactly. Substrate crossover and accumulation of protons as well proton transfer. Okay. Can somebody tell me what is SOFC and MCFC?
Solid oxide. It is
Fuel cell.
SOFC, and
Correct.
MCFC. It is molten carbonate fuel cell.
Very good. Nicely heard to my all points. Thank you so much. These are all the answers. Most of you have said it rightly. Thank you very much. I give a special thanks to Dr. Kanimori. Yeah, if there are some questions, I can attempt it.
So any questions from the participant sets?
Madam, I am Rajan from University College of New York.
Yeah.
Which type of fuel cell is preferable for automobile application, that is for electrical vehicle?
Yeah, for automobiles, PEM fuel cell is being addressed.
What, madam?
PEM fuel cell, first type of fuel cell, polymer electrolyte membrane fuel cell, the one which is being addressed for automobile.
Okay. Any specially funded scheme is available for electrical vehicle?
Any?
Funded project is specially available for electrical vehicle?
இப்போ நம்ம ஊர்லயே நிறைய ஒர்க் பண்ண ஆரம்பிச்சாங்க. டெஸ்லா வந்து நிறைய பர்சன்ஸ் ஆல்ரெடி விட்டாங்க. And Toyota, there are several companies that are working on fuel cell powered cars. Project பார்த்தீங்கன்னா DSA alleviating நிறைய ப்ராஜெக்ட்ஸ் இருக்காங்க.
That is common law, particularly for electrical vehicles. Fuel cell
ப்ராஜெக்ட் நிறைய பண்றாங்க.
Thank you.
Thank you, Dr. Rajashekharan, sir. So any other questions from the participant side? Kindly, the participants
Yeah,
are...
somebody is asking, is MFC based desalination is a cost effective one? Yes, it is.
Yes.
It is definitely. Because you don't require electricity. Okay, so it becomes a cost effective process. Yeah, it is a very promising technology.
So thank you for your wonderful session, ma'am.
Thank you, ma'am.
What is expecting lifetime of MFC, ma'am? This is the question from Madhuri.
Yeah, right now we have tested the silver-based membrane MFC for 6 months and above in the laboratory condition. We expect to improve that. The one which gets degraded is a membrane. Membrane da pokum, வேற எதுவும் போகாது. Membrane மட்டும் மாத்திரமா இருக்கும். அது வந்து you can remove it and then put a new one. Okay, fresh one போடலாம் இல்ல இதையே regenerate பண்ணி திருப்பி போடலாம். But as of now 6 months and above it is working. Silver based membrane.
Thank you, ma'am. Thank you for your wonderful, clear presentation for each and everything. You gave a nice demonstration. What is the advantage in that material and what are the disadvantages? How to overcome that with the statistical data and the research group you are having, and you are working towards the sustainability of fuel cell, especially in microbial active membranes. Very nice to hear your presentation and your work, ma'am. Wish you all success and proceedings. Wish to reach many horizons, ma'am. Thank you so much, and thank you for all the participants.
Thank you, ma'am. Thank you so much. I'll take a leave. Thank you.
Thank you.